Thank you for tuning in to watch the next video in our on-demand webinar series. Today we will be covering the world of MOLYKOTE specialty lubricants and the compatibility with elastomers. This overview will cover the basics of lubricant formulation, how base oil and additive chemistries interact with elastomer seals, and what to keep in mind when selecting the right solution for you. A quick intro on today's speaker, William Fick. Will has a degree in mechanical engineering and serves as a lubricants application engineer for the MOLYKOTE team. Will, passing it on over to you.
So first, I want to take a moment to discuss MOLYKOTE, who we are, and the different product families and solutions that we have. On the right side of the slide, you can see our MOLYKOTE wheel. It helps as a reminder to provide load, environment, temperature, and speed, which are the key characteristics in identifying your application. So based on these LETS conditions, as we call them, we can utilize one of these 6 product families you see around the circle. So greases, paste, oils, compounds, dispersions, and anti-friction coatings. Each one of them have a strong suit in one of these 3 friction regimes that you see on the left. So there's the boundary friction, mixed friction, and hydrodynamic friction. Hydrodynamic friction is typically low load, high speed applications that allow for fluid film separation between the 2 substrates. And on the left side, the boundary friction, you have high loads, low speed applications, typically, which result in surface-to-surface contact. So this is where you're going to want to rely heavily on solid lubricants, things like pastes and AFCs, to ensure that your surfaces are separated and you can reduce wear between those substrates. And then in the middle, we have mixed friction, which is where we'd usually use greases with solids or dispersions, something that works in both sides of this friction range. So let's dive into compatibility. What is elastomer compatibility? Well, when an elastomer and a lubricant in this case come into contact, there can be adverse effects. Things like volume change, durometer change, and tensile strength change, as well as many other mechanical property changes that might not be good for your application. The contributors to this are vast. Looking at just the lubricant side, we have oils, thickeners, additives, whatever else might be in that lubricant. Each one plays a separate role. Same thing with the elastomers. Based on the chemistry, the formulation, the types of substrates, there might be cross-linking involved in the formulation. All of this we've seen plays at least some role in compatibility. And then you have the environmental side, which is pretty much everything outside of the lubricant and the elastomer. Things like the application itself. Is it dynamic? Is it static? Is it a corrosive environment? Are there other chemicals involved? Maybe the temperature and duration are different. So what is good and what is bad? Well, every application is different, and that's why having a chart that says excellent, good, doubtful, do not use isn't always the best way to go. We always try to recommend testing for your specific application. For example, what amount of volume change is detrimental? Can you allow for shrink? Can you allow for swell? Sometimes we actually induce swell in applications in order to seal better, but you might not allow any shrinkage. So if it shrinks, you're going to create a leak path. So these are just things that you kind of have to think about when you're trying to determine what type of compatibility you're looking for. I also highlight that there's many compatibility charts that exist. These should really be used as tools to narrow down a selection and not necessarily a yes or no for a specific material. There's just so many different options out there, so many different variations, that I try to take them with a little grain of salt. So most often the lubricant is being selected after as an afterthought. So compatibility testing should always be conducted before you move to the application into production. So let's focus on the lubricants contribution. First, I just kind of wanted to highlight what the composition of different lubricants are. Typically, with a grease, it's mostly base fluid. With a paste, you see mostly solids. And really throughout compounds, greases, and paste, they all really share, the oils and fluids are the one that they share across the board. And then their additives and thickeners are kind of separated out. So just looking at greases alone, I just wanted to highlight how many different possible combinations there are. I mean, if you're looking at the quantity in them, the specific chemistries for each of the base oil, thickener, additive, you might have multiple base fluids in one grease. There's really just millions and millions of possible combinations. The reason I want to highlight this is because this is why it's so critical that you test and you don't just follow some generic chart online. So looking at the oil contribution, it does appear to be the primary contributor when with elastomer compatibility. Many factors seem to play a role: viscosity, the chemical structure, primarily the type though. So polyalpha olefin, mineral oil, PFPE, silicone, etc. Not all base oils are made the same, and I highlight that in these charts. So we tested two separate types of silicones and two separate types of PAO lubricants in addition to some others. But EPDM and PAO in every guide that you look at will say, no, this doesn't work. Well, our PAO type 1 follows that. However, the PAO type 2 seemed to actually do better than some of the other lubricants that we tested outside of PAOs, which is kind of a shocking difference there. And then with silicones on silicones typically don't perform well, but you can see our silicone type 1 had bad performance, but then our silicone type 2 from a volume change perspective had almost no volume change, even outperforming the PAO type 1. Focusing on the thickener, we looked at the exact same formulation with a lithium versus a polyurea. You can see that there is some difference. However, based on the scale of this graph, it's very, very little. However, this is just one situation, lithium versus polyurea. There's many other different thickener technologies out there that could have a far greater difference in compatibility. Focusing in on solids and additives, we looked at two separate anti-corrosions. Both of these were done at a very small value of 0.1%. And you can see here that the anti-corrosion 1 actually performed worse than anti-corrosion 2. So this was just kind of to highlight that even when selecting for the same type of performance benefit, you can strongly impact the elastomer compatibility. So if you're designing for compatibility or selecting a lubricant for compatibility, some just are better in with certain substrates than others. So that's another thing to kind of look at or speak with an application engineer if you're trying to get some specific test values. So on the elastomer side of things, there's a lot of contributors as well. Elastomer variation, there's different formulations. Some are formulated for high wear, high temperature. This can have a change in the durometer, which can result in different uptake of oils, resulting in different swell values. There's different processes for creating these elastomers. You have different shapes, O-rings, sheet material. Some materials are cross-linked, which make them more resistant to chemicals and make them more compatible. One example of this is with the PAO in the EPDM sheet on the top graph. You can see that the sheet material performed far better than our O-ring material. This is likely due to the sheet material being cross-linked. And it's also worth noting that you'll have variation from supplier to supplier for elastomers. An EPDM made by one may not be the same as an EPDM made by another. Everyone has different additives that separate their product from the rest. So focusing in on some of the environmental contributions, two of the big ones that we evaluated were temperature and duration. So when using sheet material, we evaluated at room temperature, so around 25°C, 65°C, and 125°C to get some of the differences. You can see some odd behavior when looking at the Buna N. We actually seen the volume change go down at 65°C from room temperature and then back up at 125. So knowing the temperature of your application can really help you determine which elastomer lubricant combination is going to work out best. And then we did a short duration test, 3, 5, and 7 days, where we evaluated volume swell after soaking the material. The worst case materials, such as PAO with EPDM, showed less change between 5 and 7 days. Some of these remain very flat from 3 to 7 days, and then there's others that could continuously trend upward or downward over time, moving past that 7-day mark. So some of the materials seem to stabilize very quickly, while others we haven't tested out that far to see how much they change. And then there's some of the other potential factors. So contamination being a big one. Perhaps there's other chemicals involved that could be causing some type of reaction, which makes elastomer compatibility worse. Perhaps there's corrosion, dynamic versus static application. So if it's dynamic, you might be creating additional heat or even wear patches that allow for more uptake of fluid into the elastomer. So that goes into the damage to elastomer, creating additional leak paths or more surface area for the lubricant to come into contact with. All of these things can likely play a big role. And if you have many bad factors together, then your lubricant and your elastomer aren't going to perform very well in your application. So I just wanted to highlight some of the things to be aware of when you're doing your elastomer and lubricant selection so that you can have the best success in your application. Thank you.